in our last lecture we have derived the Bairstow method for extracting a quadratic factor from a given polynomial. This quadratic factor may give us two real roots or it may give a complex pair of roots. We have shown that the approximations would be obtained from evaluating what is the values of h1 and h2, the increments for the initial approximation. This is the formula that we have derived last time for finding these values of h1 h2, so that the next approximation can be obtained as pk plus 1 is pk plus h1 and qk plus 1 is equal to qk plus h2. Now, we have also seen that there are 6 quantities to be evaluated at the point pk qk. All these quantities to be evaluated at pk qk, and to derive these 6 quantities we had used the synthetic division procedure, and the synthetic division procedure that we had written was this particular procedure, in which we have written all the coefficients of the given polynomial. If there are any missing coefficient, we will insert a 0 over there. Then we have applied the synthetic division by using the factors minus p minus q, and the first row of the synthetic division of the first level would give us b0 b1 b2 bn minus 2 bn minus 1 bn, and the second level of the synthetic division will give me c0 c1 c2 cn minus 2 cn minus 1. Based on the formulas that we have derived earlier, we have found that these are the formulas that can be written for these 6 quantities. We can also write down what are these quantities h1 h2 from this. We can pick up the value of h1 from here. I can insert these quantities and write a formula for that also. Alternatively, I can obtain these 6 quantities independently, substitute in this formula to get my next approximation. For example, if I substitute these quantities in this, what I would get will be simply this. Let me write down what is your h1. So, h1 is equal to, I am writing from this formula, I will just keep it here. This is minus of r partial derivative with respect to q minus s partial derivative with respect to q divided by the denominator that we have obtained earlier, sp rq. This is the value of h1 and this is the value of h2. We have the same denominator and the numerator is s into the partial derivative of this, or the partial derivative with respect to p divided by rp sq sp rq. So, what we would now like to write down is to write these quantities that we have derived over here in terms of this bn minus 1, we have written bn minus 1 these quantities. Therefore, if I do that, I would get here h is equal to minus of, I would write down this as minus r is equal to, you can see r is equal to bn minus 1 and so on. So, I am just writing them and multiplying it out. I will give you what this quantity would be. It would be cn minus 3 bn minus 1 cn minus 2, denominator will be cn minus 2 square minus cn minus 3 cn minus 1 minus bn minus 1. The denominator is rp sq minus spr, yeah, this will be both are p, yes, this is p, and h2 obtained from here is minus of bn minus 1 cn minus 1 minus bn minus 1 minus bn cn minus 2 divided by the same denominator cn minus 2 squared cn minus 3 cn minus 1 bn minus 1. The denominators for both are the same. The numerator is here bn minus 1 cn minus 1 minus bn minus 1 minus bn cn minus 2. Now, as I was mentioning to you earlier, we can use either one of these formats. Either we find out the 6 quantities from the synthetic division directly and substitute it here, or alternatively I can use this particular formula. Now, let us take an example to illustrate this particular way of obtaining the quadratic factor. I will write the, I will keep this here if you note down. So, let me write down this as an example. We will perform 2 iterations of Bairston method. Perform 2 iterations of Bairston method to extract a quadratic factor x squared plus p x plus q from the given polynomial p n x is x cubed plus x squared minus x plus 2 is equal to 0. N of course is equal to 3 here, in this case n is equal to 3. Use the initial approximations. We are giving here the initial approximations for carrying out this procedure. P 0 is minus 0.9, Q 0 is 0.9. Then find the deflated polynomial. Find the deflated polynomial. So, after finding the root to the required accuracy, we will perform the synthetic division, the first level of synthetic division, and that will give us the deflated polynomial, that is b naught x to the power of n minus 2 plus b 1 x to the power of n minus 1 and so on. So, we would perform the synthetic division using the coefficient that we have over here. Let us take these coefficients. The coefficients would give us, let me just put it here, this one. So, the coefficients are 1, then we have 1 here, minus 1 here, 2 over here, 1 1 minus 1 and 2, and we have to use the opposite signs of this, minus p naught minus q naught, minus p minus q. So, I have to use here 0.9 0.9. So, I perform the synthetic division with respect to this. Therefore, I have get here 1, that is equal to b naught. This is your p minus p 0 minus q 0 minus 0.9, yes, this will be minus 0.9, because we are performing the extracting the factor x square plus p x plus q. So, we will be performing the synthetic division with minus p 0 minus q 0. So, this is p naught into b minus p naught into b, that is 0.9. So, there is nothing here, therefore, 1.9. 1.9 into 0.9. So, we will have here 1.71, then minus 0.9 into 1. So, I will have minus 0.9. This is these two product. We add these two, we will get 0.19, which is our B2, which is our B2. Then I multiply 0.9 with the current minus 0.9, that is minus 0.171, and I multiply minus 0.9 into 1.9, that is minus 1.71. We add it, we will get 0.119, that is equal to B3. So, the first step of synthetic division procedure is complete. Now, we proceed to the next step. So, I will again get 1, that is equal to C0, 0.9 into 1, that is 0.9, add it 2.8, that is C1, then 2.8 into 0.9, that is 2.52 minus 0.9, minus 0.9 into 1, add up 1.43, that is equal to C2. Therefore, these are the quantities that we have for now evaluating our H1 and H2. So, let us evaluate H1 here itself. So, H1 is equal to, what I would do here is I will put here n is equal to 3 and write down this particular formula for H1. So, if I put that n is equal to 3, what I would get here is minus B3 C0 minus B2 C1 divided by C1 square minus C0 C2 minus B2. So, maybe I will just put it over here on this slide, so that it is easier for you to have a look at it. N is equal to 3, this is B3 C0 minus B2 C1, this is C1 square, this is C0 C2 minus B2. Now, let us first evaluate it so that we can have the other quantity. So, this comes out to be, I will give you the value of this, I have value here with the minus sign, the numerator is 651 and the denominator is 6.22. So, that I have this value as minus 0.1047. Now, I would use the quantities for evaluating H2. For a moment, let me just put this H2 over here. I am putting here n is equal to 3 in all these quantities and deriving this particular quantity. So, that quantity will be, I will have here minus sign B2 into C2 minus B2 minus B3 C1, denominator is the same, C1 square minus C0 into C2 minus B2. This is B2 into C2 minus B2 minus B3 C1, denominator is the same. So, if I evaluate this, the denominator is the same, this is 6.22 and the numerator comes out to be 6410. So, that this is 0.1031. So, these values have been used it, and the values that we have here is, we can see that B0, B2, B3, C0, C1, C2. So, these are the quantities that we are using over here. Now, I need the next approximation, that is equal to P1 is equal to P0 plus H1, that is 0.9 P1 we started with minus 0.9 and I have here a here is a minus sign. So, I have this as minus 0.1047, that is equal to minus 1.0047 with a negative sign. Yes. Then Q1 is Q0 plus H2 and Q0 was 0.9, this is plus 0.1031, this gives me 1.0031. So, H1 is minus 107 and H2 is 1031. So, this is P1 is minus 0.9 and Q1 is equal to 0.9. So, we add up and we have this required approximation. Now, I perform the next approximation. H2 is no sorry, this would be a plus. The minus, there is actually there is a minus sign here also, there is a minus sign here also, there are two minus signs. Now, we will perform the synthetic division with respect to these two quantities. So, let us again write these coefficients. So, let us put a line here, then let us write down 1 1 1 2, this is 0.9 minus 0.9. So, this is sorry, I think I will use this space will not be sufficient, let me use the next sheet, this is not correct. So, let us again write this as 1 1 minus 1 2 and we are taking it as minus P1, that is 1.0047 minus 1.0031. So, with that we will have again 1, that is equal to B0 and multiply these two 1.0047, there is nothing over here, this is 2.0047, multiply these two quantities 2.0141, the 1 into this, that is minus 1.0031. So, add up all the 3, I produce 0.010, that is equal to B2. I multiply this and this to give me simply 0.011 and I am multiplying these two quantities to give me minus 2.0109. We add up to give us 0.02. 2. Now I proceed to the next step. I will have 1 that is equal to C naught, 1 into this 1.0047, there is no quantity here, that is equal to 3.0094, that is equal to C1. I am multiplying 3.0094 by 1.0047, that is equal to 3.0235, and 1 into this, that is minus 1.0031. We add up to give us this quantity, that is equal to C2. Now we have obtained this quantity C naught, C1, C2, B naught, B1, B2, B3. I will substitute in the previous values of H1, H2, and I will drop the computation. You can just verify that. I would get the values of H1 is 0.0047. I get the value of H2 as minus 0.0031. So that the next approximation would be P2 is P1 plus H1, that is minus 1.0047 plus 0.0047 is equal to minus 1.00. And let me write down the next value. The next value now we have Q2 is Q1 plus H2, and Q1 is 1.0031 and H2 is minus 0.0031, and that is 1.000. Therefore, the quadratic factor that is extracted is x squared plus px plus q, that is x squared minus x plus 1. And it so happens that this is also the exact quadratic factor. Here we are able to get the accuracy because the H1 plus H2, already you can see the required accuracy has been obtained, and the exact solution of the problem is exact factor is x squared minus x plus 1. Now let us look at the second part of the question to get the deflated polynomial. So let us write down the first step of the synthetic division. So I will have this is 1 1 minus 1 2 the coefficients, then minus p, that is equal to 1, and minus q, that is equal to minus 1. This is minus p minus q. So I have this is b naught, 1 into 1 2, that is equal to b1, 1 into 2, that is 2, minus 1, that is equal to 0, that is equal to b2. We do not need the last part because the deflated polynomial will be is b naught, that is equal to b naught x plus b1, b naught x plus b1, that is equal to x plus 2. The deflated polynomial is b naught is simply x plus 2. So we have now extracted all the three factors. The linear factor has been obtained, so that root is x is equal to minus 2 is also obtained, and this you can see it gives us a quadratic, it is a quadratic factor. Therefore this gives us the, from here we are going to get the two roots. The two roots we can find the normal way. This is a complex pair. So the what is this complex pair? This is 1 plus minus root of 1 minus 4 by 2. So what we are really getting here is the complex pair. We are getting this complex pair from this particular value. So when once you obtain the quadratic factor, the complex pair that is obtained from here, and the whatever is left out would be the deflated polynomial, on which we can again use the same method to get the quadratic factor, but if it is finally a odd polynomial we will land up into a linear polynomial. This is how we can apply the Beer-Stokes method to extract a polynomial. In fact, this is the most commonly used method in the software that is available currently on your computers. The Bairstow method is the most popular method for it. Yes, B2 we don't, it is a cubic equation and we are extracted a quadratic factor, therefore what is left out will be a linear polynomial. So it will be simply b0x plus b1 will be the deflated polynomial, 2 units less than the degree that we started with. Now we would give a method, a direct method, which of course is not available on the computer software, but it is an interesting to know how a method can be applied sometimes when you have a real and distinct root case, and it is easy to apply that particular method. It is a direct method. This is a direct method, and the method is called the Grafè's root squaring method. It is called the Grafè's root squaring method. The idea behind the Grafè's root squaring method is very simple. Suppose we will consider the case of only real and distinct roots. We will take the case of real and distinct roots. Suppose that a polynomial has got roots say 1, 2 and 5. Let us take this as a simple example. Then we shall determine a polynomial whose roots are squares of these roots. So a new polynomial will construct say q1 whose roots are squares of this, 1 square that is 1, 2 square that is 4, 5 square that is equal to 25. We will see that we are going to put a negative sign for each one because of the reason of deriving it, but essentially you can talk of magnitude of the squares. Then I will find another polynomial using the same procedure whose roots are squares of this previous one, that is now 1 square that is 1, 4 square that is 16, 25 square 625. Then I go on doing it this root squaring procedure. I will have this. What happens is after a few steps of this root squaring procedure, the roots are separated by large amount. The ratio of the leading one, this one, is very large compared to ratio of these ones. Therefore, we will make the simple rule, use the simple rule of finding the roots of a polynomial given that sum of roots is this quantity, product of two roots taken at a time is this. We know the simple formula for a polynomial. We shall just use that to obtain the approximation from this polynomial, and that is because the roots gets separated so much that the ratios, the lower ratios will be insignificant compared to the ratios that we have. Now let me illustrate this how we get this particular thing. So let us start with our polynomial Pnx. So that is your a naught x to the power of n, a1 x to the power of n minus 1 plus so on a n minus 1x plus a n. What I will do, I will take all the even terms to the left, odd terms to the right. So, or odd terms to the left, even terms to the right, one of the way. So, you will have the even terms on the left hand side and we keep odd terms on the right hand side. Alternatively, we can keep odd terms on the left, even terms on the right, and that is starting with the first one. This is n is even, let us say, then x to the power of n is even, x to the power of n minus 2, x to the power of n minus 4, these will all be on one side, and x to the power of n minus 1, x to the power of n minus 3, they will all be odd, they go to the other side. So, what we will therefore have here is a naught x to the power of n plus a2 x to the power of n minus 2, I will write down one more, x to the power of n minus 4 plus so on, and then I square both sides. So, I do squaring on both sides. So, this is a1 x to the power of n minus 1, a3 x to the power of n minus 3 plus so on square. So, I take the even and odd terms to the right hand side and left hand side and then square on both sides. Then I simplify it, bringing now everything to the left hand side. So, I would therefore have a naught square x to the power of 2n, that is first term, Then we will have x to the power of 2, because we have squared it, x to the power of 2n minus 2 is the next term. X to the power of 2n minus 2 will be contributing from here the square of this, and the cross product of these two will give you x to the power of 2n minus 2. That means I will have here on the left hand side 2 times a naught a2, from the right hand side I will have minus a1 square. So what I would therefore will have is a1 square minus twice a naught a2, x to the power of 2n minus 2. So I am collecting the coefficient of x to the power of 2n minus 2 on both sides. So the contribution will come only from these two from the left and this from the right. Then I would write the next term x to the power of 2n minus 4. Now you can see 2n minus 4 comes from the square of this as we move from the left to right. So this will give you 2n minus 4, then it will also, this gives you 2n minus 4. So one term on the right hand side is coming to the left. This cross product a naught a4 is 2n minus 4. So there will be two terms from the right and from the left, and one term from the right that we will have. What are those terms? a2 square 2n minus 4 cross product 2 times a naught a4, and this product coming to the left minus twice a1 a3 x to the power of 2n minus 4 plus so on, alternatively positive negative, and finally we will land up with minus 1 to the power of n a n square is equal to 0. Now we have put minus 1 whole square a n square, depending on whether we have got even terms on the left or on odd terms on the right, the suitable sign of this is taken care of. What we do here is we said that I need a polynomial whose roots are the squares of the previous roots. Therefore in this I will substitute, I will let z is equal to minus x squared. In fact I am now taking the opposite sign of the square of the roots. So in magnitude it will be square of roots. So I substitute z is minus x squared. If I do that, we are substituting z is equal to minus x square in this. So this will be x square to the power of n. So x square to the power of n means minus z to the power of n. So a naught square into minus 1 to the power of n z to the power of n. So the first term will read here a naught minus 1 to the power of n z to the power of n. So I substituted x squared is equal to minus z, therefore I will have minus 1 to the power of n coming from here. Then I will have minus a1 square twice a naught a2, this will be x square to the power of n minus 1. So I will have minus 1 to the power of n minus 1 z to the power of n minus 1. This is minus 1 to the power of n minus 1 z to the power of n minus 1 a1 square minus 2 a naught a2. So the next term will be a2 square, yes correct a naught square, a2 square minus twice a1 a3, I am writing this first, twice a naught a4, I will have minus 1 to the power of n minus 2 z to the power of n minus 2 plus so on, minus 1 to the power of n a n square is equal to 0. So let me remove this now. So what we will have is this. Now I can remove minus 1 to the power of n throughout. You can see this minus 1 combines with this to become minus 1 to the power of n. This is same as minus 1 to the power of n. Minus 1 to the power of n is common throughout. So that I can remove that and write this as a naught, okay, let us use a notation, b naught z to the power of n plus b1 z to the power of n minus 1 plus b2 z to the power of n minus 2 plus so on, bn is equal to 0. So that b0 is equal to a0 square, b0 a0 square, b1 is a1 square minus twice a naught a2, b2 is a2 square minus twice a1 a3 plus twice a0 a4. and so on. Bn is an square. Now this is a polynomial of degree n whose roots are the squares. We have substituted z is equal to minus x square. The roots of this are the squares of the previous roots with an opposite sign. Therefore, if the original equation has got roots xi1 xi2 xi1, say the if you take xi1 xi2 xi(n) as the roots of p and x, the original equation, then the roots of the new equation are minus xi1 square minus xi2 square so on minus xi(n) square is the roots of new equation, roots of the new equation. Now interestingly, just as we have put the synthetic division procedure in a formal way, in a nice synthetic division procedure, here we will put it in a tabular form and show how we can get all these coefficients without really looking into the polynomial. Now if you look at the let me write down the coefficient, then I will explain the logic behind how we are going to write it. Let us first write down all the coefficients in the formula. The coefficients in the p and x are let me write it here, that is equal to a0, a1, a2, a3 so on an. All the, if you look like at this, all these coefficients have got the squares of the previous coefficients in the first term. So I will have here a0 square, a1 square, a2 square, a3 square, an square. Now if you look at this next coefficient, this is the product. You take any particular theorem, that means location here, we take the neighbors, nearest neighbors of that, multiply it with an opposite sign with a 2. So if I have a0 square, there is no neighbor on the left hand side, therefore there will be no term below that. Here I have a neighbor on this side a0, a neighbor on this side is a2, therefore I will have multiply this and an opposite sign to it, I will put minus twice a0 a2, I will put minus twice a0 a2. Now there is no other neighbor available to me on this side, so there will be no more term below this. I take a2, a2 has got neighbor a1 a3, so it will have a twice a1 a3 coming from here. Then the next neighbor is available to me, a0 on this side, a4 on this side, but they all go with a alternative signs, plus minus so on. So next one will be a positive sign 2 times a0 a4, the next neighbor is available. So for this, no next neighbor is now available on the left. So I go on putting this sequence in this fashion, and here when I reach the last one, there is no neighbors for it at all, so there is nothing. So I would now this just add it up, this will be my b0, this will be my b1, this will be my b2, b3 and so on bn. Now you can see, for this root squaring procedure we really do not have to look into it. It is just take that particular location, look at its neighbors, what all is available neighbors, write down its cross products with plus the suitable sign plus minus, add them up, that will give you my b0, b1, b2. Now let us say we have done m squarings. Let m squarings be done. Now the final polynomial, let us take it as b0. Without loss of generality, let us put back the coefficient as some x to the power of n, b1 x to the power of n minus 1, b2 x to the power of n minus 2 plus so on, plus bn is equal to 0. So the last one that we are doing it. Now since we have done the m squarings, each time the roots have become squares of each one. So, after m squaring the root will become xi these xi i's to the power of 2 to the power of m with an opposite sign, Therefore, the roots of this, if you call this as Ri, let us call this roots of this equation, If you take these roots of this equation as this, then these roots should be Ri must be equal to opposite sign xi I 2 to the power of m, I is equal to 1 2 3 n. Now, since the roots are real and distinct, if I take the magnitudes of this root, the magnitude I can arrange the roots in the magnitude from highest to lowest. So, this root will be much larger than this root will be much larger than this root, and this root is be much larger than Rn. So, we are arranging them in the descending order with the largest magnitude at the top and this. For example, in the we have taken 1 to 5, we find that after 2 iterations 625, 16, 1. So, we are now arranging the roots of that new equation finally in the order of R1, R2, R3 of that final equation. I would now use the simple idea that the sum of roots in a polynomial is equal to minus b1 by b0, that is our formula, ordinary the polynomial equation this. Therefore, the sum of the roots Ri is equal to minus b1 divided by b0. Then we know that sum of the roots taken 2 at a time will be b2 by b0. So, this will be sum of Ri Rj is equal to plus b2 by b0, I not equal to j, of course, taken roots taken 2 at a time. Now, what we will do, we will write the remaining ones. Since the roots are far separated, I would approximate this as R1, the leading root. For example, in the example which I have taken 1 16 625, I will approximate the sum of the roots as 625, that is what it means. So, when we do few more squarings, the last root, the biggest root is the order of some 10 to the power of 15, the next root is of the order of 10 to the power of 5 or 6. So, the ratio of this is so big, we will approximate as this, and this we will approximate R1 R2, next root R1 R2, so on. We would, I will for example Ri Rj Rk will be minus b3 by b0, and this I will approximate R1 R2 R3, and the last one will be the product of all the roots is equal to minus 1 to the power of bn, we have put it as bn. We will have the sign, suitable sign we have to insert, whether it is positive, whether it is even or odd polynomial. So, minus 1 to the power of n bn divided by b naught. Now, from this we have a very simple rule of getting my root. R1 is approximated by the first one, right. Now, let us take the ratio of the successive coefficients, R1 by R1 R2 divided by R1, that will be R2, and what is that ratio? That is b2 divided by b1 with an opposite sign. Now, I will take next these two. If I take the ratio of these two, R1 R2 gets cancelled, I will get R3 will be minus b3 divided by b2. So, I am getting now approximation for R1 R2 R3 sequentially I am getting. Therefore, I am getting the ratio Ri will be equal to minus bi by bi minus 1, that is simply these coefficients with an opposite sign would give you the approximation. I will put this previous slide here. From this equation, now I will be able to straight away write down what will be my required approximations for this. When once I write this one, I will find out what its magnitude. Magnitude of this is magnitude of Bi by magnitude of Bi minus 1, and this will be magnitude of xi I to the power of m. Each root is the 2 xi I to the power of 2 to the power of m. So this is the simple equation from which I must find out what is the value of the xi I approximation. So let us take the logarithm on both sides. If I take the logarithm on both sides, this I will write it first 2 to the power of m outside logarithm of this. So I will have 2 to the power of m log of magnitude of xi I, and logarithm of this is log of magnitude of Bi minus log magnitude of Bi minus 1, and or alternatively logarithm of magnitude of xi I is 2 to the power of minus m into logarithm of magnitude of Bi minus logarithm of Bi minus 1. Therefore, the root is obtained now. It is going to give us the absolute value of the root. So we are getting the absolute value of the root. Absolute value of the root is obtained. Now we need to find its sign. The sign is obtained by substituting in the original equation. The sign of this root is obtained by substituting in the given equation. By substituting this value in P and X. Now an indicator as to when you should stop. Of course we can do some 2 squaring, 3 squarings and so on. An indication when the root squaring procedure should be stopped would be, if you look at back this particular table we have formed, when the contribution of these cross products becomes small compared to this a2 squared, then the next equation, the contribution, this equation is almost identically same as the previous equation, because the contribution of this is almost negligible. That means a stopping procedure is that we can see that the contribution of the cross products is negligible compared to the square, previous square. That means a stopping criteria would be, you can use that particular idea. Stopping criteria is when the contribution of the cross products is negligible, or let us just call it as small, is negligible compared to squares. Of the previous coefficients, compared to squares of the previous coefficients. I would just show a slide for you to, I mean you need not note it, I will just show you how the terms that would come out. I am taking the, let me take it out, I will take an example, I will put it here. I mean just observe, I will just make an observation for here only, you may not note this. The equation that I am considering here is 11x minus 6 is equal to 0. This is the equation that is given here. What I am writing these coefficients as we have written it over here, just write it, see it over here. This is your a1, 1 minus 6, 11 minus 6, that are the coefficients. Then I will have a 1 square, 36, 121, 36. The cross product minus 22, this cross product minus 72 with an opposite sign, add up. This is the first squaring that is done. Then I square this 196, square 49, square 36. Then the cross product for this is the product of these two and this, 2 times 49 with an opposite sign, 2 times 14 into 36, this one, and this is the next value. So this is your second squaring. Then I square 98, square this, and this is the fourth squaring. I will just pull it a little bit top. Now you can see, as I was saying, as we have go this number of squarings, these numbers are going to be enormously small and they get separated very fast. Now what I would therefore require is the formula that we had written it over here. So I then use this particular formula straight away on these coefficients. This is my B0, B1, B2, B0, B1, B2, B3. So I would now take the ratios of the required ratios and then take the, depending on the number of squarings that we have done, here we have done squarings 4. So I will have here 2 to the power of minus 4. 2 to the power of minus 4, xi1 is log B1 minus log B0. So I will take the logarithm of this minus logarithm of this divided by 16 will give me the logarithm of the absolute value of the first root. So just as an illustration I would give you, because very difficult for you to copy this. So with this, if I do that, what I am getting is this particular value of the table. So this is the final value that we have. The successive approximation to the roots, this is the first squaring, second squaring, third squaring, fourth squaring, and this is first root alpha 1, alpha 2, alpha 3. As I said, this is equal to B1 by B0, this is B2 by 0 with divided by 16, and this is B3 by B2 divided by 16 in the last case. In the first squaring we are dividing by 2 to the power of 1, that is 2. Next squaring we are dividing by 2 square, 2, that is 4. In the third squaring we are writing 2 cubed, that is 8. In the last squaring we are dividing by 2 to the power of minus 4, that is your 2 to the power of minus 16. So I am talking about this particular quantity, division of this particular quantity. So this table value is obtained, and you can see the exact root for this is 3 to 1 is the exact solution of this particular thing. But of course it is, for writing it manually it is okay, but if you go to the computer, when once these larger numbers are encountered, there will be lot of round of error, there will be problems. Therefore this direct method is not usually in the computer software, whereas the BESTO is the most popular method that is used in the software. If you take any software, find the obtain the roots of this equation, all the roots of the equation, the method will say that they have used the BESTO method. Now before we closing, let us make few comments on what we have done so far on this particular topic, because we will be completing this topic and next time we will be starting the another topic. So what we have done here is the few methods for finding the roots of nonlinear equation. The first method we have done is bisection method, which would never fail. We are never using the value of the function in bisection method, we are using only its signs, but it is very slow. What is the accuracy that we obtain? Each time we are getting a factor of division by 2, that means in computer language we are getting a 1 bit of accuracy in each iteration. Getting 1 bit of accuracy is too low for us, and it is therefore it is very slow, even though it will never fail. Then we have given regular falsi and secant methods. Regular falsi method also would never fail, because the root should lie in the interval that we are considering. Therefore we are always, the root is always within our interval, therefore we will never fail, but it has got a linear rate of convergence, therefore it is again very slow. The secant method or the Chebyshev method, Newton-Raphson method, multi-point iteration methods, they all converge very fast. We know that Newton-Raphson has quadratic convergence, Chebyshev has cubic convergence, multi-point has got cubic convergence, but there must be a little compromise between the two, and the best compromise will be, if you are not sure what is happening in the solution of the problem, use few iterations of the bisection or the regular falsi. So we are sure that we have now reduced the interval to a sufficient length. Suppose you started with the length of 16, length of the interval as 16, if you have used 3 times bisection, first bisection length will be reduced to 8, second bisection will be reduced to 4, and the third bisection will be reduced to length 2. or even sufficient for us to do two bisections or regular falsing. Then we jump over from there to a very powerful method like Newton-Raphson or Chebyshev method, so that the convergence would be very fast. That is one way of tackling the problem where you do not have any knowledge of what is happening in the solution of the problem. Now if all the roots are required in a polynomial, then the only thing is we have Bayer-Stokes method that should be done. A lot of experiments have been done with Bayer-Stokes method and try to find out when Bayer-Stokes method may fail. The Bayer-Stokes method fails only in one situation, and that is a very artificial situation, and that is, let us take the polynomial which has got only one real root but all complex pairs. Let us say you have polynomial degree 21, 20 are complex pairs, 1 is the real pair. Now you are choosing your initial approximation to the quadratic factor, coefficients in the quadratic factor x square plus px plus q. Now choose it artificially that x square plus px plus q vanishes at the roots that should get obtained. Let us suppose 1 was one of the roots. Now choose your px and q, x square plus px plus q, such that it vanishes at x is equal 1. Now since x square plus px plus q is a quadratic factor, it cannot extract a quadratic factor because you have made it forcibly to be 0 at the only real root that exists. Therefore this is the only situation where Bayer-Stokes will fail, but then we have a solution for it. The solution is multiply it by x, that means make it an even polynomial. That means if you multiply by x, you are providing one extra root, x is 0. Now make it extra 0, now apply the same approximation which you have done in the previous case, now it will definitely converge. Why? We have now introduced a real pair by introducing x is equal to 0, and 0 and 1 is a pair now. Therefore this x square plus px plus q will converge in just 1 or 2 iterations because it has now got a pair, 0 also has a pair. So 1 and 0 will come and it will never fail. Therefore the best way, if you are doubtful whether the equation has got only one real root and your approximation may be becoming 0 at that root, just make the given polynomial as a even polynomial so that the method would never fail. Therefore as I was saying, the software that is there available to you often uses this particular idea, that try to make it as a even one. Of course there are various other improvements in the software when they have made it very powerful software, but this is the basic idea is using the Bayer-Stokes method. Okay, thank you. We will stop today.